Hi, Assalamualaikum warahmatullahi wabarakatuh. We have come to the final lesson of semester 1, chapter 7, Ionic Equilibria, lesson 41, Solubility Equilibria. Today we are going to define solubility, molar solubility, and solubility product KSP, and then calculate KSP from concentrations of ion and vice versa. Then we have to predict the possibility of whether precipitation occurs or not by comparing the values of ion product QSP. After that, we are going to define and explain the common ion effect and perform calculations. Solubility S is the ability of a substance to dissolve in a solvent. The solubility of a solute is the concentration of the saturated solution for the solute. In other words, it is also a quantity that dissolves to form a saturated solution. The unit is gram per liter. There's also a unit if we multiply them by the molar mass. It will become mole per liter or molarity. The greater the solubility, the smaller the amount of precipitation. That would help you understand what solubility is. Let's look at the definition even more in detail. When a substance dissolves, a slightly soluble salt forms a saturated solution at room temperature. So in a saturated solution, an equilibrium exists between the solid state and its dissolved ion. For example, barium sulfate solid dissociate or ionize to become barium ion Ba2+ aqueous and sulfate ion aqueous. So we can see that in the beaker, there is a part at the bottom where there is a solid, the ionic solid. So you can see in the right picture, the ionic solid is represented by the anion and cation bubbles. And then outside of the precipitate, you can see the water molecule. The water molecule in red and white band shape is attached to the cation and to the anion. So it shows there that the ions of barium and sulfate are dissolved in water. But the equilibrium exists between the ions and the precipitate. So there would be a dynamic balancing there in the beaker. What is a saturated and unsaturated solution? A saturated solution contains the maximum amount of solute that can dissolve. So in the beaker here, we can see the undissolved solute remains at the bottom as precipitate. What about unsaturated? An unsaturated solution does not contain all the solute that could have dissolved in it. So it stays as a solution that doesn't have precipitation and have some more room for other solute to come in and dissolve. Each of any salt or ionic compound which is slightly soluble have their own KSP. KSP is the equilibrium constant for the equilibrium between an ionic solid and its saturated solution. Solubility is the mass of solute that dissolves in a given quantity of solvent to form a saturated solution. We've seen the unit is gram per liter. or kilogram per centimeter cube, or gram per centimeter cube. Whereas if we use the molar mass, we're going to get molar solubility, the number of mole of a solute in 1 liter of a saturated solution, mole per liter. For example, silver chloride, the equilibrium equation for the salt dissociation, it is reversible. AgCl solid becomes Ag plus aqueous plus Cl minus aqueous. Notice that starting from now, all the balance equation, we must put the phase. It is very critical. What is the Kc for this equation? Kc equals to concentration of Ag plus multiplied by concentration of Cl minus divided by the concentration of AgCl. For orange owners, this Kc is correct. But for green course book owners, it missed out the concentration of AgCl. Can you please add it there at your page 214? Thank you. But since we know that the concentration of the solid is constant, therefore we can include them with the constant Kc. So it becomes Kc multiplied by concentration of AgCl equals to concentration of Ag plus times concentration of Cl minus. Again, for green course book owners, the concentration of AgCl is missed out there at the first line in page 215. Please add it. For orange owners, it is correct. But the second line is not correct for orange owners, because now when Kc multiplied by AgCl, which is a constant, it becomes a different constant. That particular constant we called Ksp. So for orange owners, there is AgCl over there. Remove that one. Cross out that one. That's not, should be there. So Ksp now is concentration of Ag plus multiplied by concentration of Cl minus, whereby Ksp is the solubility product constant. Indefinite. Solubility product is the product of the molar concentrations of the ions involved in the equilibrium, each raised to the power of its stoichiometric coefficient in the equilibrium equation. So now we're going to learn how to develop the Ksp for certain salts given in the question. I think it would be more comprehensive if we straight away look at example 7.20. Write the expression for the solubility product of silver chromate Ag2CrO4. Firstly, we need to write the balance equation. Ag2CrO4 solid will dissociate reversibly to become 2Ag plus aqueous plus CrO4 2 minus aqueous. Notice that for all the balance equation that we're going to deal with after this must have the phase. The exponents in the equilibrium constant expression for Ksp are the coefficient in the balance equation. Therefore, the Ksp would be the concentration of Ag plus to the power of 2 multiplied by the concentration of ion CrO4 2 minus. There goes all the formula that we have seen in previous slide. The next part is for you to do practice 7.6. Write the expression for the solubility product of magnesium fluoride, argentum carbonate, calcium phosphate, magnesium phosphate, argentum sulfate, zinc chloride, argentum sulfate, and ferrum hydroxide. Here is listed the solubility product constant Ksp for selected ionic compounds. You can see the aluminum hydroxide has 3 times 10 to the power negative 34, but that's not the smallest number. The smallest one is silver sulfide. It's 8 times 10 to the power of negative 48. So, silver sulfide is the less soluble salt among all these ionic compounds. So, what does Ksp values tell us? The smaller the Ksp, the less soluble the salt. Let's do example 7.21. The solubility of plumbum iodide is 1.2 times 10 to the power of negative 3 mole per dm cube. Calculate its solubility product Ksp. Assuming that the solubility of PbI2 is an unknown S, we are able to make a simplified ice table here because we want to know the stoichiometric coefficient of each ion. Pb2 plus is a plus S and I minus is a plus 2S. So we know the Ksp expression is concentration of Pb2 plus multiplied by the concentration of I minus to the power of 2, again given as is the value 1.2 times 10 to the power of negative 3 molar. We insert the value S given from the question. Ksp now is equals to 1.2 times 10 to the power of negative 3 multiplied by 2 times 1.2 times 10 to the power of negative 3, and this one will be to the power of 2. So press your calculator. The answer would be 6.912 times 10 to the power of negative 9 molar to the power of 3. Example 7.21, let's do question number 2. The solubility product Ksp of calcium carbonate at 25 degrees Celsius is 2.8 times 10 to the power of negative 9 molar square. Calculate the solubility of calcium carbonate in gram per decimeter cube at this temperature. So we need to use the molar mass now. For this question, it's the other way around. We are given the Ksp and we want to find S. So we do the simplified ice table like the previous question. Calcium carbonate solid dissociate reversibly become Ca2 plus aqueous plus carbonate ion aqueous. The stoichiometric coefficient is 1, 1, 1. So we're just going to use S. Assuming the solubility is unknown S there. So given is the Ksp expression. The expression will always give you 1 mark. So don't lose that mark. And you're going to get, when you substitute the value, 2.8 times 10 to the power of negative 9 is equals to S square. And then we square root the value and we got S as 5.2915 times 10 to the power of negative 5 molar. This is the molar solubility because the answer is in mole per decimeter cube. So, we find the molar mass of calcium carbonate, that is 100.1 gram per mole. We multiply it with the value of S molar solubility that we have found just now. And the final answer is 5.2968 times 10 to the power of negative 3 gram per decimeter cube. Notice the unit. Okay? To test our understanding, practice 7.7 is for you to do. For orange course book owners, the final answer is not written in the book, so you can copy it down from these slides. Question number 1, 2, 3, 4, 5, 6, and 7. As a bit of a conclusion or recap here, we can say that S is used to indicate solubility, and solubility is calculated per mole of salt, not the molarity of each dissolved ion. So 2 ions per formula is going to be S square, and when we have 3 ions per formula, it's going to be 2s squared multiplied by s. That would become 4s to the power of 3. So the relationship between KSP and solubility at 25 degrees Celsius is given to you in this table, but we don't need to memorize the formula here, since we're going to do the questions individually one by one. The next part of the lesson is how to predict precipitation if we have a mixture of 2 solutions. So we need to be able to know or predict whether precipitation will occur or not. So it depends on the ion product, Q. The solubility equilibrium equation for a slightly soluble salt Ma is shown in this balance equation. We use alphabet to represent the unknown. MXAY solid becomes XMY plus aqueous plus YAX minus aqueous. So the KSP would be the concentration of ion My plus to the power of X multiplied by the ion AX minus to the power of Y. If we mix a solution containing M plus ions with one containing A minus ions, the ion product QSP is given by the concentration of ion My plus to the power of X multiplied by the concentration of ion AX minus to the power of Y. QSP has the same form as KSP, but the concentrations of ions are not at equilibrium concentrations. So we are able to predict whether precipitation occurs or not. When we have calculated the QSP and it turns out that it is less than KSP, these are the conclusions. The solution is unsaturated solution. There will be no precipitation of the salt. More salt should be dissolved to increase the ion concentration until QSP is equal to KSP. The system will proceed from left to right. Please make the correction there, both in orange and green book. If QSP is turned out to be same as KSP, the solution is a saturated solution. No precipitate will occur. Equilibrium exists between undissolved solid salt and its ion. And if the QSP calculated is more than KSP given in the question, the solution is actually a supersaturated solution. Precipitation of the salt occurs. The system will proceed from right to left. Again, please make this correction both in orange and green book. Thank you very much. This is a simplified note from the previous slide. For unsaturated solution, Q is less than KSP, so there is no precipitate formed. For saturated solution, Q is equals to KSP. Also, there will be no precipitate formed. But for supersaturated solution, Q is more than KSP. There will be precipitate occur in the beaker. Let's do example 7.22, question number 1. If 500 milliliters of 0.014 molars of calcium chloride is added to 250 milliliters of 0.25 molar of sodium sulfate, will a calcium sulfate precipitate form? So notice that the cation is from calcium chloride, the anion is from sodium sulfate. So we need to calculate the number of mole of each ion. Okay, the first thing that we need to do is to find the number of mole of calcium chloride using MV, whereby the molarity given in the question is 0.014 multiplied by the volume is 500 ml, so that would be 0.5 liters. This is 7 times 10 to the power of negative 3 mole. Remember, this one must be in liter. If you want to use ml, you need to do mv over 1000. Now, what is the concentration of calcium ion? This would be 7 times 10 to the power of negative 3 mole divided by the volume of the total 500 with 250. That would be 0.75 liters. This is 9.333 times 10 to the power of negative 3 molar. Okay, the next step would be to calculate the number of mole of sodium sulfate. Also MV, so what's the concentration? 0.25 molar multiplied by what's the volume is 0.25 liters. This is 0.0625 moles. Now the concentration of sulfate, that's the one that we are dealing with, is 0.625 moles divided by 0.75 liters again, and we're going to get 8.333 times 10 to the power negative 3 molar. So we got the concentration of each ion for the salt that we are going to predict whether it can precipitate or not. So let's do the balance equation of calcium sulfate solid. Ca2 plus is the ion in aqueous plus sulfate ion aqueous. So this is the balance equation, and you're going to do the KSP expression, which is Ca2 plus concentration multiplied by SO4 2 minus, and let's insert the values that we have calculated. For calcium is 9.333 times 10 to the power negative 3 molars multiplied by 8.333 times 10 to the power negative 3 molars. And this will give you 7.7457 times 10 to the power of negative 4 molar square. Sorry, this is not KSP, this is QSP because KSP is given here. We need to compare. Which one is smaller? KSP is smaller. So QSP is bigger, 7.7 compared to KSP, 2.0. So what is the conclusion here? Calcium sulfate will precipitate the reaction will move, reaction position is from right to left. So please write this down in your page 217 or 219. Example 7.22, question number 2. 50 ml of 0.001 molar sodium hydroxide is added to 150 ml 0.01 molar magnesium chloride. Will a precipitate form? Given Ksp for magnesium hydroxide is 2 times 10 to the power of negative 11. Okay, firstly, as we have done before, we need to find the number of mole of sodium hydroxide, 0.001 molar, multiplied by the volume in liters, 0.05 liters. This would give you 5 times 10 to the power of negative 5 mole. And the concentration of OH minus, how do we know it is OH minus? Magnesium hydroxide. So hydroxide comes from sodium hydroxide there. So that would be 5 times 10 to the power of negative 5 mole divided by the total volume, 50 ml plus 150 ml, that would be 0.2 liters. This is 2.5 times 10 to the power of negative 4 molar. Alright. The next one is we find the number of mole for magnesium chloride. It is 0.01 molar multiplied by 0.15 liters. Then this would give you 1.5 times 10 to the power of negative 5 mole. And what is the concentration of magnesium? Mg2 plus. It is 1.5 times 10 to the power of negative 5 mole divided by 0.2 liters, the total volume, and you will get the answer 7.5 times 10 to the power of negative 3 molars. Okay. The next step is for us to write the equation. Magnesium hydroxide, the formula molecule is given here, so it would be no problem for you. This phase is in cis, solid, and then magnesium 2 plus is the ion. The ion is in aqueous form, plus 2OH minus. The stoichiometric coefficient here is 2 because we have 2OH minus since the charge of the cation is magnesium 2 plus. So what is the QSP? The QSP would be the concentration of magnesium ion multiplied by the concentration of OH minus ion to the power of 2. So the concentration that we have calculated just now for magnesium is 7.5 times 10 to the power of negative 3 multiplied by the hydroxide concentration ion is 2.5 times 10 to the power of negative 4 there. Molar. For the second one, for hydroxide ion here, we need to do to the power of 2. Okay, so your answer would be, press your calculator. Okay, that would be 4.6875 times 10 to the power of negative 10 molar to the power of 3. Okay, so now what is the conclusion? Let's compare the values. 2 times 10 to the power of negative 11. And this one is 4.68 times 10 to the power of negative 10. So this one is bigger. QSP is bigger than KSP. So you can say magnesium hydroxide will precipitate. The reaction will proceed from right to left. Okay. Example 7.22, question number 3. A solution is 1.5 times 10 to the power of negative 6 molar in nickel iron. Sodium carbonate is added to make the solution 6 times 10 to the power of negative 4 molar in carbonate iron. The KSP for nickel carbonate is 6.6 times 10 to the power of negative 9. So will nickel carbonate precipitate? For this question, it is simplified for us because the concentration of nickel ion and carbonate ion is already given. So we straight away do the balance equation. Nickel carbonate in solid form will produce nickel ion in aqueous form together with carbonate ion in aqueous form. So the QSP would be, write the expression first, nickel 2 plus multiplied by carbonate ion. Let's substitute the information given in the question. 1.5 times 10 to the power of negative 6 molar is the concentration for nickel ion. And 6 times 10 to the power of negative 4 molar is the concentration of carbonate ion. And we got 9 times 10 to the power of negative 10 molar square. This is smaller than KSP given. The KSP is 6.6 times 10 to the power of negative 9. This one is negative 10. So it is smaller. The conclusion is QSP is smaller than KSP. So NiCO3 will not precipitate. Reaction will proceed from left to right. Here is practice 7.8 for Orange Course Book Honours. Please write down the answer for all the 4 questions. We have come to the last part of the lesson, common ion effect. Common ion is an ion that is the same to 2 or more components in a mixture of a solution of ions. Common ion effect is the reduction in the solubility of salt in the presence of a common ion. Consider a saturated solution of silver chloride in water. The solubility equilibrium is given in the balance equation AgCl solid becoming Ag plus aqueous and Cl minus aqueous. But when NaCl is added to the saturated argentum chloride solution, the concentration of Cl minus aqueous ions increases. Cl minus ion now is the common ion. You can see the sodium chloride salt dissociate completely to produce Na plus aqueous and Cl minus aqueous. What will happen to AgCl solid precipitation in the solution if we add a common ion Cl- from the sodium chloride. We can see that here the chlorine ion will be dissolved in the water, making the solubility of AgCl decreases until the product is once again equal to Ksp. Therefore, the addition of common ions will reduce the solubility of a slightly soluble salt in its saturated solution. Less solubility for silver chloride there means that more AgCl will precipitate. Why? Because according to Le Chatelier's principles, the increase in the concentration of Cl- will cause the position of equilibrium shifting to the left, making some AgCl to precipitate. So the solubility of AgCl will decrease until the product once again equal to Ksp. Addition of common ions will reduce the solubility of slightly soluble salt in its saturated solution. Let's do example 7.23, question number 1. The solubility of silver chloride in pure water is 1.3 times 10 to the power negative 5 molar. What is its solubility in seawater, where the concentration of chlorine ion is 0.55 molar? Ksp of AgCl is given 1.8 times 10 to the power negative 10. Compare the solubility of AgCl in pure water and seawater. Explain. The first thing that we need to do is to write the balance equation. AgCl solid becomes Ag plus aqueous and Cl minus aqueous. And then we are going to do an ice table for solubility. Initially, the solubility for Ag plus is 0. And now in seawater, the concentration of Cl minus is 0.55. The change is plus S and plus S. Now the equilibrium is S and 0.55 S. Okay, so what we're going to do is insert the values of Ksp into the expression. Ag plus is S, Cl minus is 0.55 S is very, very small. So 0.55 plus S is almost equals to 0.55 because we want to try to drop this S since the value of Ksp is very small. Now it becomes Ksp equals to 0.55 S. Insert Ksp, 1.8 times 10 to the power negative 10. It is 0.55 S. So what is S? S is 3.3 times 10 to the power of negative 10. So in the question, we are given S for AgCl in pure water is 1.3 times 10 to the power of negative 5 molar. By comparing between the two S, solubility of AgCl in seawater is very small compared to the one in pure water. So what is our conclusion? AgCl is much less soluble in seawater. Example 7.23, question number 2. Calculate the solubility of copper 1 iodide in water and 0.05 molar of sodium iodide, given the KSP is 1.1 times 10 to the power of negative 12. The solution is, firstly, you write the balance equation CuI solid becoming Cu plus aqueous plus I minus aqueous. The initial concentration is 0 and 0. There is no common ion yet because this is in pure water. So the change in the equilibrium is S and S respectively. What is the KSP? 1.1 times 10 to the power negative 12 molar square is equals to concentration of copper ion times concentration of iodide ion. That is S square. So S, the solubility is 1.05 times 10 to the power of negative 6 molar. The second part of the question is we are given the common ion of I minus 0.05. So in the ice table, we put 0.05 in initial, and at equilibrium, it becomes Cu plus S, I minus 0.05 plus S. We assume S is very small, since KSP is very small. 0.05 plus S now is 0.05 only. So we substitute the values. KSP is equals to 1.1 times 10 to the power of negative 12. That is equals to the concentration of copper ion multiplied by the concentration of iodide ion. This is equals to S times 0.05 molar. S now is 2 times 10 to the power of negative 11. So, when we compare the S from both situations, it turns out that copper iodide would become more soluble in pure water. Without common ion, in pure water that is, solubility S is 1.05 times 10 to the power negative 6 molar. But with 0.05 common ion, the solubility now is 2 times 10 to the power of negative 11 molar. It is very much less, the solubility. Therefore, it will precipitate more. Example 7.23, question number 3. What is the solubility of calcium fluoride in 0.025 molar of sodium fluoride solution? KSP given is 6.2 times 10 to the power of negative 8 molar square. This is important if you want to work in a toothpaste factory. Let's write down the equation and ice table. Initially, calcium ion would have 0. Fluorine ion would have 0.025 molar. The changes is S for calcium and 2S for fluoride ion because the stoichiometric coefficient for it is 2. Now the equilibrium concentration would be S and 0.025 molar plus 2S. Let's substitute the values into the KSP expression. 6.2 times 10 to the power of negative 8 equals to concentration of calcium ion times concentration of fluoride ion. So S multiplied by 0.025 molars only, since we assume S is very, very, very small. That one in the bracket must be to the power of 2 because the stoichiometric coefficient for fluoride ion is 2. So 6.2 times 10 to the power negative 8 divided by 0.025 to the power of 2 is equals to S. And when we press the calculator, the answer is 9.92 times 10 to the power of negative 5 molar. Example 7.23, question number 4. KSP for HCl is 1.7 times 10 to the power of negative 10 molar square. Calculate the molar solubility of HCl in water and in a solution of 0.1 molar potassium chloride. Let S be the molar solubility of argentum chloride in water. You can see the simplified ice table there. KSP is equals to concentration of Ag plus times concentration of Cl minus. So we are given 1.7 times 10 to the power of negative 10 equals to S square. S is now 1.3 times 10 to the power negative 5 molar. This is the solubility of silver chloride in water. Now, what is the solubility of silver chloride in 0.1 molar of potassium chloride, where chloride ion here is the common ion? Let's say we use the unknown Y. Now, the simplified ice table would be Y for argentum ion and Y plus 0.1 for chloride ion. Insert the values into the KSP expression and you got this. By assuming Y is very small, 1.7 times 10 to the power of negative 10 is equals to 0.1 Y, where Y is equals to 1.7 times 10 to the power of negative 9 molar now. Thus, the solubility of silver chloride in 0.1 molar of potassium chloride is 1.7 times 10 to the power of negative 9 molar. Here we can say the solubility of silver chloride, of course, will decrease in the presence of chlorine ions because it is the same ion competitively. Let's do practice 7.9. In red color is the final answer for this question. Green owners and orange owners, write them down. Thank you very much. Alhamdulillah, we have finished lesson 41 on solubility equilibria, and I hope you would do a good job studying for your finals. Thank you very much for paying attention and watching the video. I will see you again next semester, inshallah. Assalamualaikum warahmatullahi wabarakatuh. Bye.